So Alex is a research associate in the particle physics group at the University of Manchester. He's both an experimental and theoretical physicist. What I'll do is I'll stop the share. I will hand back over to Alex. And if you want to add anything about that brief summary that I've given, and then get started with your presentation.
Yeah, no, that was a lovely introduction. Thank you very much. Hello, everyone. Like I said, Fraser very nicely said, I'm Alex, and I've been an RA at Manchester now for about a year. Before that, I was working for the University of Mississippi, and before that, I did my PhD at Liverpool. So I'm very much tied into the UK system. But yeah, I'm going to give you a brief introduction to my work on two experiments. Well, the main experiment at Fermilab, the Muon g-2 experiment. I also work on the mu2e experiment at Fermilab, which is part of Fermilab's Muon program. Okay. And hopefully I'll be able to give you enough information in the presentation such that when we get to the tour, you'll know kind of the basics of how the experiment works, the principles, and that will give you more of a platform to ask any questions that you like when we get round to the tour and I show you the different parts of how the experiment works. So let me go ahead and share the presentation. So yeah, so this presentation will be about 30-40 minutes about the Muon g-2 experiment at Fermilab, which is an experiment that has been running now for, this is just starting as of potentially tonight if they switch the accelerator on like they plan to. This will be the start of the 4th year, but it's a program that's been going back since its inception stage in the early 2000s, and there were pre-experiments that have that did similar measurements before that I'll explain, and the basis of which is to measure this property of the Muon g-2. So let's talk about muons at Fermilab. So at the end of 2009, some of you may know that the big experiment at Fermilab up until that point was the Deviation. And the Deviation was a collider experiment, a proton-antiproton collider experiment, which was running from the mid-90s up until 2000s, and made some amazing discoveries, one of which was the top quark, and did amazing measurements of the W mass and also set the groundwork for the discovery of the Higgs at CERN. But that program ended in 2009, and suddenly there was a lot of equipment and this huge accelerator complex available for different studies. And as I said, it's the beam that's created is a p-bar beam, an antiproton beam, and it was decided the best thing to do with that was to use it to make some other daughter particles, in this case muons. And so in 2011, the Deviation did its last collisions, and Fermilab then moved to its new Muon program, and has built since then a Muon campus that houses two experiments: the mu2e experiment, which is the first one I work on, and the Muon g-2 experiment, which this talk is about. And you can see here, this picture on the left is the downstream, kind of the last end of the accelerator beam line, where you have the recycler ring, which is where the proton bunches are formed. And then you have a delivery ring, a debuncher ring, which is to make sure that the beam, I'll explain all this in detail later, but to make sure the beam's pure. And then once we have the muons that we need, they're delivered to the Muon campus. So this is the back end of Fermilab. I don't know how many of you have seen Fermilab before, but hopefully you can all see my mouse here. And this building here is Wilson Hall. And the accelerator beam line starts all the way back here in the distance and comes through underneath Wilson Hall. And then you have the entire accelerator complex living under here. This is a booster ring here, which is for accelerating the protons up to, this is the 3rd stage in the accelerator complex. And then back all the way around here, you can see that this is the old Deviation ring here, this river. But behind this picture here is the main injector recycler ring, which is where we get the bunches, the proton bunches. This kind of triangular shape here is the delivery ring, and then that delivers the beam into the two buildings here, which is the Muon campus. And if I zoom in here, you can see that this is the Muon g-2 building, what we call MC1, and this is the mu2e building, which is MC2. And the Muon g-2 building houses the experiments currently running. The mu2e building, MC2, is being built at the moment and will start running once the Muon g-2 is finished, because they need to use, they will both use the same muon beam, so they can't necessarily run at the same time. So you could ask then, well, why would we want to build a Muon campus at all? Well, we know that the standard model of particle physics has many flaws or missing pieces. We know that we can't incorporate dark matter. There's the hierarchy problem. You can't incorporate gravity into a quantum explanation of particle physics. There's matter-antimatter asymmetry, and so on and so forth. And so theorists have spent a lot of time developing models and ideas to explain these things, and to also, explore the possibilities of many other more exotic scenarios, things like extra-dimensions, Kaluza-Klein models, dark photons, and any wild examples that you can think of. And the idea from an experimentalist point of view is that we want to test these theories to either, directly measure some effects, that are a product of these models, or to look at the standard model and say, okay, if we understand that the standard model is slightly incomplete, let's probe the standard model to the best precision that we can to test it and see if we can niggle out something that's missing. And so these are these two approaches to experimental particle physics. You have direct searches for new physics, which are like the collider experiments like the LHC. And at the moment, now the Higgs has been discovered, they're doing their best they can to try and produce supersymmetric particles or anything of the like that they will observe directly as a signal against their background. And then the Muon G1s2 experiment and others are in a camp of experiments called precision and intensity experiments, where they indirectly search for new physics. And they do that by taking an observable that we understand to know very well, and they try and test the limits of that by measuring it as precisely as they can, and then comparing that with what we expect the value of that observable to be from the theoretical prediction. And here are some examples of experiments like the indirect search experiments that are going on across the world now, and the things that they're looking for. So the questions that can be answered are, is lepton number conserved? And so, for example, the mu2e experiment at Fermilab will look for a neutrinoless conversion from a muon to an electron, which will violate lepton number. You have the origin of matter-antimatter asymmetry in the universe. And things like the EDMs of fundamental particles are parity violating processes, and so then will give it signs of those effects. Sorry, I'm getting flashes at the bottom of my screen that's taking my gaze. And then then there's what is dark matter, and so there are two experiments that are looking for that. On the right, the bottom right, there's the ADMX experiment and the Lux experiment that are looking for those. And then we have these deviations from standard model predictions, and so G-2 is one of those. And like I say, there are some others there, but what we're doing there is looking at a standard model observable, measuring it using that experiment, and then comparing it to the theoretical prediction. The other question you can ask is, why muons? Why do we think that muons are a good tool to probe the standard model? Well, first of all, muons are very easy to produce. And you can see that here, that if we have pions decay almost 100%. The branch ratio from the pion decay to muons is almost 100%. And if we have a proton beam, well, then pions are a very easy product to make from proton beams. And so at Fermilab, we use the proton beam to produce pions, which then decay into muons, and then which we use to do our measurements. In general, muons aren't susceptible to strong force interactions. Hadronic interactions are a problem because they can't be calculated perturbatively, and so they are susceptible to high uncertainties, and so we're removed from those. Muons have a relatively long lifetime, which we can actually then extend by using time. Obviously, we can use time dilation by speeding up the muons in the G-2 experiment. And then they're relatively heavy, which means they're able to probe new physics interactions better than, say, an electron would, because they have a higher mass. They have more energy there to lend to particle interactions that the electron necessarily wouldn't. And so all of these are good reasons why muons should be used to test new physics. And so Fermilab built this program and such that the Muon G1X2 experiment would run now to test the standard model. The mu2 experiment would then run after. But then in between those two experiments can be used for side measurements, like measuring a mu or EDM, or other charged lepton flavor violating processes. And you can see some of those potential processes that we could search for in these Feynman diagrams in the bottom right hand corner here. So now let me come on to the basis of Muon G1s2 and talk about magnetic moments, what we're measuring. And so in the classical explanation, magnetic moments, or historically magnetic moments, have been used for the last century as a way to probe physical interactions. In the classical description, the magnetic moment mu is dependent upon the charge, the mass of the particle, and its angular momentum inside a magnetic field. And the torque, that magnetic torque, can be given by the cross product of the magnetic moment and the magnetic field that you applied. And then you can also get the magnetic potential as the dot product of that magnetic moment with the magnetic field vector. So then if you then upgrade that slightly, so you have a particle with a spin like a fermion, like an electron or a muon, then what you see is that the magnetic moment then depends on the particle spin itself. You have S here, which is obviously the spin vector that is dependent on the Pauli matrices, and then the muon, the magnetic moment of fermions then is proportional to that spin. But it has a proportionality factor, G, which is called the gyromagnetic ratio, which describes the strength of the spin-orbit coupling to the magnetic moment. That is to say, it's the strength of how much the magnetic moment will cause the particle to precess around its spin vector. So when you have a particle that has a spin vector in a magnetic field, as you can see on the right here in this diagram, the particle will precess around its spin vector. And that G factor, the gyromagnetic ratio, gives you the strength of that proportionality constant. Okay, and then you can see here in the bottom right hand corner you have the spin frequency there, omega s, which is then dependent on that gyromagnetic ratio as well. So that's in a classical example. When you then move to a quantum expectation from a classical expectation, well, in the classical expectation, the expectation is that the gyromagnetic ratio should equal 1. And then there were the Stern-Gerlach experiments in the 1920s that showed that the gyromagnetic ratio for electrons actually equaled 2, such that the electron, or the muon in this case, precessed twice as fast as expected in the classical case. And this was shown to be true in 1926 by Thomas when he incorporated his relativistic treatment into quantum mechanics, and was then incorporated into the Dirac equation in 1928, where you can see here you have this magnetic potential term included here. And actually from that, you can show that the Dirac equation predicts that the gyromagnetic ratio should be equal to 2 for spin half particles. Now, this was obviously a big step in the early 1900s, and so it inspired a program of measurements for people to measure the G factor of other particles known at the time, one of them being the proton. And so Stern and Esterman set out to make that measurement in 1933. And there's this famous quote from Pauli to Stern where he said, well, come on, it's obvious. The G of the proton has to be equal to 2. Well, and then they measured it, and the G of the proton was 5.6. Okay, and this was the first anomalous magnetic moment in some sense, right? And then a bigger surprise came later on, where you would say, okay, well, magnetic moments can only be susceptible to charged particles, or only charged particles should be able to have a magnetic moment. But then in the same year, Rabi inferred that the magnetic moment of a deuteron, which is a neutral particle, has a G factor of -3.8. And it was asked, well, how could that be the case? And of course, now we know that that's the case because these are composite particles. Okay, it took 30 more years after that to develop the quark model. And it's the composite components of the deuteron and the proton, the quarks themselves, that contribute to the magnetic moment. And this was a big step in itself, but it showed even at that time that magnetic moments were a very powerful tool for exploring whatever is the new physics at the time. And that has continued from that point up until this day. So let's go a step further now, and let's look at relativistic quantum field theories like QED, for example. So up until 1948, Dirac had it sussed. Okay, the G of the electron was 2, and that was it. Until Cushtion-Foley in 1948 did an atomic spectroscopy experiment and actually found that G deviated from 2 ever so slightly. So you can see this 2.00238 with a with an uncertainty of 6 times 10 to the minus 6. And so actually the gyromagnetic ratio of the electron differed by 2 by about 0.1%. And at that time, there was no explanation why. We understand that to be a manifestation of the fact that particles, they're never really alone. They exist in a vacuum, but that vacuum has its own expectation energy, and particles like electrons will interact with that vacuum and cause virtual particle interactions, i.e. they will create virtual particles that will take their bare observables, things like their mass and their coupling constant, and the interactions with the vacuum will cause those values to deviate slightly to what we call the physical masses or the physical couplings or the physical observable values. And in this case, this is coming on to why the muons are important, but the more massive the particle, the more mass it has to lend, and the probability for an interaction is higher. So you can imagine that, muons have more energy there or more mass there to be able to produce more exotic virtual particles than the electron would. This can be thought of as the virtual particles, they effectively screen the interaction, so they change it, as in the muons, the bare muon can't see the effect because the virtual particles are screening it. And so in the case of the gyromagnetic ratio, it changes that G factor slightly because it doesn't see exactly what the bare value is. And we for the anomalous magnetic moment, which is the quantity that we're measuring in the Muon G-2 experiment, this is this expression at the bottom. You can see A mu, and we define that to be the gyromagnetic ratio -2/2. So G -2/2, which lends the name to the G-2 experiment. So that is exactly the quantity that we're trying to measure in the G-2 experiment. Okay, the deviation of the gyromagnetic ratio from 2 due to its interaction with virtual particles. So obviously Cushing-Foley had measured that, but at the time, in 1948, there wasn't really a good description of why that was. And the first description came in the same year when Schwinger calculated this diagram here. This is the one loop diagram that shows here that you have an electron, an external electron that exchanges a virtual photon. And he showed that interaction gave a deviation from 2 that was expressed exactly by this constant here, alpha over 2 pi, okay, which was approximately 2.0232, which agreed very well with Cushing-Foley's measurement in 1948. This was the first real confirmation of a relativistic quantum field theory, the first real confirmation of QED, and set QED in, as a standing for the basis of the standard model that we see now, and showed that we can't just look at particles in terms of their bare interactions or tree level interactions. We have to take as many higher order terms as we can to get close to the physical observables that we want to see. Now, this here was the first, for the magnetic moment, was the first real comparison of the experimental measurement versus the theoretical value, and is the basis of what the Muon G-2 experiment is trying to do today. There is obviously a theoretical value for that prediction, for that value that we have from the standard model, where we've taken all of the different parts of the standard model and added them all up, and we get this number that deviates from 2 slightly, and we're trying to measure it as precise as we can to compare to that number to see if there's a significant deviation. And of course, like I say, virtual photons aren't the only virtual particles. And so let's see how much that value can deviate from 2, or does deviate from 2 when we calculate it. So in Dirac's theory, experiment G is 2 and the theoretical G is 2. So this is just, the point where we have quantum mechanics with the Dirac equation, and we have, relativity and matter and antimatter. And then suddenly we get QED, and we get Cushing-Foley, and we get Schwinger, and we get his alpha over 2 pi contribution from this one loop exchange photon, and this changes this value by, this much. Then we can incorporate now up to this point QCD, and you can see that even then they're starting to deviate, right? We get experiment here, and we get theory here, and already theory is slightly smaller. And then we can incorporate the electroweak interactions from weak coupling photon particles like the Z boson or the W or the Higgs, And again, you can see that this is starting to deviate even more. And then suddenly we get to the point where at such precision now, we have this deviation whereby, if you can see in this left-hand plot, if the experimental value that we see here is at 0, and the theoretical value here from the standard model is here, we have this deviation of about 300 units, okay? Between the anomalous magnetic moment of, this is in the case of the muon, between experiment and theory. And the question is, what could be causing this deviation? Could it be the fact that we're missing supersymmetric particles? Could it be the fact that we're missing dark matter contributions? Who knows, okay? But at this point, the deviation is there, and I will get on to quantifying that a bit more in the next slides. So let's talk now specifically about the muon G1s2 and the status of the muon G1s2 in terms of theory and experiment, and what we're hoping to do experimentally over the next couple of years. So what have we said so far? We've said that we have a magnetic moment, which is dependent upon the spin-orbit coupling and the gyromagnetic ratio G, that we have the Dirac equation predicts that G equals 2, but due to higher order radiative corrections or loop contributions, G will deviate from 2 by this factor 2a mu. So there are quantum corrections inherent from relativistic quantum field theories like QED in the standard model that cause these values to deviate. And in some sense, you can imagine that these effects manifest themselves differently if you're calculating them theoretically, or if you're trying to measure them experimentally. And so from the theory side on the left here, we have Schwinger's first calculation of the anomalous magnetic moment being alpha over 2 pi, which was this deviation here. And so what that is, when you do the full calculation, they are all corrections to the QED vertex function. Okay, so the vertex function here being, if this is a muon, you have a muon here interacting with a photon. This is a muon photon vertex. And so you need to correct those to a higher order as you can, the one loop contribution of a photon, and so on and so forth. And you determine those to the highest order that you can in the standard model, such that you have a sufficiently precise calculation. Now, the experimental measurement I will get onto in detail, but what we're trying to measure is something called the anomalous precession frequency, which is the difference between the spin frequency of muons and the cyclotron frequency of muons, and that's proportional to the anomalous magnetic moment. Okay, and so we're trying to measure that value, and then we'll compare that in the experiment with the theory to test the standard model. So the status that we're at right now in terms of what are the best predictions and what's the best measurements out there are that the Muon G1s2 theory initiative has spent the last 4 years putting together a big collaborative effort to try and pin down this theoretical number, and have done it exceptionally well. And the last experiment was the Brookhaven National Lab experiment in 2003, which measured the Muon G1s2, which is what its Fermilab is trying to now do better than. But if you compare these two numbers, you can see here that the difference between the experimental value and the standard model value has a difference of units of about 28 in 10 to the minus 10, but with an uncertainty of just about 8. And this corresponds to a 3.7 sigma discrepancy between the two values. And we all know that discoveries in physics are set at the 5 sigma level, and so we're now just off a sigma below what would be classed as a physical discovery. Okay, so what we're trying to do now at Fermilab is to remeasure that value, but 4 times as precise as the BNL measurement, so that when we compare those two numbers with that increased precision, we can say definitively whether there are beyond the standard model contributions to the anomalous magnetic moment. And that would be the first, if that was to be the case, that would be the first confirmation of beyond the standard model physics from experiments around the world so far. So in terms of the theoretical prediction and the standard model, these are the steps, these are the different calculations that we need to do, right? So there are the 3 main sectors of the standard model. There's QED, electroweak, and hadrons. And the QED contributions are the majority of it, okay? So we now know these up to 5 loops. That's just the 5-loop contribution is nearly 13,000 Feynman diagrams. And all in, that is nearly 100% of the total standard model contribution. But QED is a perturbative calculation. We can do that very precisely. And so the uncertainty of that is very, very small. The electroweak contributions comparatively in themselves are very small, especially now we know the Higgs mass, which contributes via this diagram here. But the uncertainty, again, it's bigger than the QED contribution, but it's a very small relative contribution to the total uncertainty of the standard model, the total standard model contribution. The difficulty comes in hadrons because hadrons are non-perturbative. We don't have precise calculations of non-perturbative effects, and so we have to rely on experimental data. And there are these two classes of diagrams here, the hadronic vacuum polarization and hadronic light by light contributions, and you can see that really they contribute to 50% each of the total standard model uncertainty. Now, I'm not going to go too much more into the theory side of things. I do know a lot about it. The hadronic vacuum polarization contributions were the basis of my PhD thesis. So if you have questions about that later, feel free to ask. But I'm going to focus on the experiment to keep it on Fermilab for now, and we can come back to those later. But this is now this is pictorially the status. Okay, so you can see that here in the bottom we have all the standard model estimates from 2004 up until now, this 2020 value, and you can see they've all remained about the same, other than the uncertainty's got a bit smaller over time. And then this green band here is the Brookhaven measurement of the anomalous magnetic moment in 2003, and then this blue band is what we expect to, the precision we expect to achieve at Fermilab. And so we compare the pink band to the green band, we have 3.7 sigma, deviation. If the g-2 experiment was to stay at the same mean value, but achieve the 4 times precision that we expect it to, this will be close to 7 or 8 sigma. Okay, so it's a real effort to try and get this nailed down and understand if we can really prove whether there are beyond the standard model contributions entering here. So let me come on to the Muon g-2 experiment specifically. So how do we measure it? Well, what we want to do, of course, is we want to suscept muons to a magnetic field, and so we eject polarized muons into a magnetic storage ring. If I go back one, you can see that this is our storage ring here. You'll see this a lot of times, but we eject polarized muons into here, and this storage ring is a 1.5 Tesla magnet. It's a 1.5 Tesla B field, okay? And we store those muons in that storage ring, and we allow them to orbit round, and then we measure the difference, as I said before, between the spin frequency and the cyclotron frequency. And that is proportional to g-2/2, or this A mu factor. Now notice that if there is no magnetic moment, then G equals 2, which is the Dirac theory, and actually the spin frequency would just equal the cyclotron frequency. And what that would mean is that when the muons were going around this ring, they wouldn't precess. There would be no gyromagnetic ratios, there would be no orbit around the spin vector, and they would just orbit around. But physically, that's not true, okay? So we want to measure the anomalous, we want to measure the anomalous precession frequency to a high precision, but we know as well that we need to know this magnetic field because it is proportional to this magnetic field as well. And so the Fermilab g-2 experiment actually measures 2 quantities. It measures this precession frequency, but it also has to measure the magnetic field to a really high precision as well. And we do that using proton nuclear magnetic resonance, which I'll talk a bit about, okay? Let me talk about how we produce the muons. So we produce 2 4 times 1 trillion 8 GeV proton batches to this main injector recycler ring, okay? So this is a little graphic here. You can see that these go into the main injector recycler ring here. Then what happens is the batches are split into 4 bunches, and then they're cycled around again. And once every 10 milliseconds, you will see that one of the bunches is extracted down the AP0 target hall towards these beam lines, okay? Now once they hit the target, the protons hit the target, and that makes pions. And 3.1 GeV pions are selected, and they're focused by a lithium lens down this line, and they're transported through focusing and defocusing lenses to the delivery ring to keep them focused in the beam line. So then they go through the beam line here, and they go to the delivery ring. At this point now, we have pions, and pions are starting to decay into muons, but we probably still have some protons left as well. So we do a clever thing in the delivery ring where we allow the protons the beam as it is here to cycle around the delivery ring 6 times. What that does is that gives it a time separation effect where, because the protons are heavier, they start to lag behind. It allows all of the pions to decay into muons. Once it gets to the 6th turn, we wait for the muons to pass what's called a kicker, which is basically a magnet. It kicks out all the remaining protons and leaves us with a very pure muon beam, which we can then inject into the muon G-2 experiment. So they're focused through the beam line, injected with the storage ring, and that allows us to do that measurement, okay? And that whole cycle is repeated twice every 1.4 seconds. And we get this time structure you can see here, where you have 8 bunches here, 8 bunches here, and that's every 1.4 seconds, all right? Now, we need to know the spin of the muon, obviously, because we need to know, what the muons do, and we need to know the measurement of the spin inside the storage ring. And to do that, we need polarized muons. And so what we do is, when the muons come towards the beam line, towards the delivery ring, there's a set of what are called quadrupoles, which are basically electrostatic plates, which act as a series of lenses like you see here, which is what I said before. They keep the particles focused through the beam line. Now, the pions decay, and the muons can be produced in any random direction. All right, but if the pions decay and the momentum is such, the transverse momentum is such that the decay of the pion to the muon isn't parallel or anti-parallel to the direction of motion, well, there is too much transverse momentum for it to stay in the beam line, so they fire off. So what we end up with is the muons that are the highest energy, that are parallel to the direction of motion, or the lowest energy, anti-parallel to the direction of muon. We have nothing in between. All right, so we only ever capture the highest or lowest energy muons. Now, in the weak decay of a pion, the neutrino spin has to be opposite of the momentum, okay, from weak physics. That also means that must be true for the pion, as you can see for the muon in this diagram here. And what that does is that results in a completely polarized muon beam. And so this parity violation effect in weak decay, in the pion decay, gives us a 97% polarized muon source for free at either the highest or lowest energies, which is perfect for what we need. So then once the muons are stored, the muons will then decay into positrons, which are what we measure. Okay, they're positive muons, so they decay into positrons, and that's what we measure. Now, the positrons with the highest energy will always be emitted along the direction of the spin of the stored muon. Okay, so what we can do is say, okay, well, we have a positron spectrum that spans a range of energies. Let's cut away the ones with the lowest energies that don't sit along the direction of the spin, and then let's only measure the ones, let's only analyze the data of the ones with very high energies. And in that sense, we know the spin of the stored parent muon, because we know that the electron has decayed along the direction of the spin path. All right. Now, what happens in the storage ring as the muons orbit is that you have to boost from the muon rest frame to the lab frame, right? And what that does is it shifts the decay positron energy distribution in favor of the higher energies, if the energies are higher, or vice versa if it's anti-aligned. Okay, you have this spin precession, and so once the spin precession is aligned with the muon momentum, the energy distribution will be higher and lower the other way around. And obviously, the muons are orbiting at the cyclotron frequency, and what that means is that as the muons orbit around and we measure them, when we look at the energy distribution modulates with this g-2 frequency. The energy spectrum will modulate at that g-2 frequency as the spin vector processes. Okay, and we get this wiggle pattern, which we'll see a lot about in a minute, which is proportional to the anomalous precession frequency that we want to measure itself. That's exactly that value. So we have muons that we want to come in, and how do we store them? So muons come in through here. This is the beam line here. And because this is a 1.45 Tesla magnet, this ring, we need to make sure that we can store the muons. You put muons in a 1.45 Tesla magnet, they're going to fly all over the place. And so we have something called an inflector magnet, which is about 1.7 meter long magnet, which cancels the magnetic field in that region. So you can imagine that the signs are flipped over, and there's no magnetic field, and so they just pass straight through. And then around the edge here, much like in the the upstream beam line, we have 4 quadrupoles. They vertically focus the beam, the electrostatic quadrupoles. The magnet itself radially focuses the beam. So we have radial and vertical focusing, But what we don't have is the correct orbit. You'll see that the muons come in and they come on this red path, and then they're slightly off to the ideal orbit. So what we have here is we have 3 kicker magnets, which basically provide a tiny magnetic field that just kick the muons back onto the storage ring that the storage orbit that they want, and they exist on this blue orbit here. And then the muons can orbit around this ring happily, something like 500 times before they decay, and then we measure the decay positrons. Now, this 1.45 Tesla field, as I say, is something we need to know to a very high precision. And so to do that, the first thing we have to do is make sure that the magnet is as uniform as it can be. And we do that for a process called shimming. And shimming is basically a way that you take the magnet and you insert tiny pieces of steel or whatever your magnet's made up of to adjust the composition slightly so you can get as uniform a magnetic field around the ring as you can. And this VT that you will see here is the process from the year process from 2015 to 2016, where we did the shimming of the Muon G-2 experiment at Fermilab. And you can see this blue line is the difference in the magnetic dipole at the Brookhaven experiment in 2003. This is how it varied across the ring azimuth. And you can see that over time, this shimming, this process, the magnetic field was changed bit by bit, and it was measured, and it was slowly over time made more and more uniform, until now you'll see that it will come up towards the end, and you'll see that we actually have a very uniform magnetic field compared to the previous measurement. All right, so that's the uniformity. Then to measure it, we have NMR probes. We have 387 of them inside the vacuum chamber itself, which measures the magnetic field all around the storage volume. And then when the muons aren't in there, because you have to imagine here, if this left diagram picture here, you can see this is the center of the storage region. So the fixed probes sit all on the outside here and measure this. But what we actually need to know is what the muons see. What do the muons see in the storage region here? And so we have a trolley which we run around the ring, which is basically just a block NMR on wheels, and we run it round during the time when the muons aren't in there, and that measures the magnetic field inside the storage region, and then we convolute what the fixed probes see with the trolley, and we get a map of that storage region. Okay, and you can kind of see that here in this VT. So this shows you what the NMR probes see. This is the trolley going around. There are 17 probes inside the trolley itself, and these graphs you can see fluctuating here are all how you can see the magnetic field changing as we go around azimuth, and then we get this measurement of the dipole field here. So that maps the B field in the storage region, tells us the magnetic field to a very high precision, and allows us that to enter the calculation that we need to do. This will be what the muons see. Okay, so this is the inside of the storage region. This is a simulation that shows these on the right here are straw tracker detectors, which show us exactly which give us the beam, which give us measurements of the beam distribution inside the storage ring. And you can see that if I play this, the muons will go around. These are the quadrupoles here. You can see 4 plates here. So the muons have entered up past the inflector. These are the kicker magnets. There's one here, one here, one here. And then you can see that we're starting to store muons, right? It's because they've been kicked onto the right orbit. So they're always being focused by these electrostatic quadrupoles. They go round and round and round. And then we get more of these. And eventually you'll see that they start to decay. And at this point here, you can see that they've started to decay into positrons, and they pass through, because they lose energy, they pass through the wall there, through the trackers, into the calorimeters, and then we measure them. Okay, so this is just a small simulation that shows what the muons see as they go around the storage ring. So we're measuring this precession frequency, and you can imagine that the muons are going round and round this ring like spinning tops, and they'd have this, this precession gyroscope effect they're undergoing as they go around, and they do that as they go around the storage ring. So we're measuring this difference between the spin frequency from this precession and the cyclotron frequency, and that gives us this wiggle that you can see in the bottom right hand corner. Now, I said to you that we want to store the beam with electrostatic quadrupoles because the ring only provides radial focusing. So we have these quadrupoles at 4 locations which vertically focus the beam down, because the muons want to pitch upwards, right? They really want to just fly away. So we apply this electric field, and that keeps them there. And that means there isn't a with the focusing, it goes from something like this to something like this. But the problem with that is you know, we're focusing this beam, then it wants to fly apart again, and we're focusing again, and so we get this two-dimensional simple harmonic motion effect where the beam likes to fluctuate backwards and forwards, and those are called Betatron oscillations. All right, so we know that the beam, as it's going around, is doing this like wavy effect, and it's causing this pattern in the radial position of the beam that you can see here, and you can see it sloshing backwards and forwards. Now that changes our expression for the spin precession frequency, because we're now dependent on the electric field. And so what we can do is we can choose for this term, the electric field here, we can choose the magic momentum. So we can choose gamma equals 29.3. And that means that this term cancels this A mu term, and to first order this electric field correction goes. Okay, so we lose this term to first order. But not all the muons are and then at the magic momentum that we want. And so we have to apply a correction here called the electric field correction. And then the dot product of the velocity with the magnetic field here leads to a pitch correction where some of the muons still want to pitch upwards slightly. And so we have to correct for that too. And this is just an example to show you that, you know, these effects lead to systematics that we need to know very well. They change the beam dynamics in the ring. And so we need to be able to understand those to make sure that we understand our value for the spin precession frequency to high enough precision. Now, measuring the K positrons, I said to you before that we have calorimeters, and that the muons go around this ring, and the energy energy distribution modulates the anomalous precession frequency. So what happens is when the positrons go into the calorimeters, there are lead fluoride crystals. The positrons hit those, that produces Cherenkov light, which is then picked up by silicon photomultipliers, and we get a time and energy distribution of the K positrons, and that modulates, as you can see, this is the energy in the calorimeters, and it modulates at the spin precession frequency. And that results in this wiggle plot here where we've made this energy cut, so we only have the high energy muons, and it wiggles as a function of time. But you can see here that what we try and do is then fit this data to a model that we know it should be. So this is we call it a 5-parameter fit. And you don't need to know necessarily what all the terms are, but that this 5-parameter fit is what we expect it to be in optimum conditions. But the fit isn't good enough. You can see that the chi-square here is greater than 2, and so there must be something missing from this fit to the data. And the things that are missing are the beam dynamics. Okay, we have all these things that we're doing to focus the beam. We have the quadrupoles, we have the kick, and the beam sloshing all over the place. And so we're not just measuring the spin precession frequency, we're measuring all those effects at the same time. And you can see that by taking if you take a fast Fourier transform of and you get the frequency spectrum of the decay spectrum, you see that you get the frequency spikes of things other than the spin precession frequency. And there are, I said you have these Betatron oscillations, and so you have those horizontally and you have those vertically. And so what we need to do is in the fit function, we have to account for all of those. The 5-parameter function becomes a 17 or a larger parameter function if you're susceptible to more effects. And if you include all of those, then you get a fit that's very, very good, and you can measure this spin precession frequency very well. Now I'm coming quickly to the end, which is a good thing because I know I've overrun slightly. We want to get onto this tour, but this is just an idea of the analysis structure. You can see that we have many groups that are independently analyzing the data to get the spin precession frequency. So we have different methods, and we have things that, the methods are susceptible to different systematics, and that's good because they can all work as cross checks of each other. So they're going to be combined into one number, into this omega A value. And then we have the same for the magnetic field, which is expressed here, omega P here, which is convoluted with the muon distribution because we need to know what the magnetic field the muons see inside the storage region. And then when we know all of those, that's fed into this expression here and gives us a value for the anomalous magnetic moment. And so we're now coming into the 4th data run, and we have 3 years worth of data now. And if I go to the next slide, this will show you the data that we've taken. So this is the run 1 data up until 2019. We had run 2 years ago, and then this year was just run 3, and we're just starting run 4. And you can see that we've already taken over 7 times the data that was taken at Brookhaven. And hopefully we're still at the end now of analysing the run 1 data, but we're hoping to publish that in the coming months. and then the other two data sets will follow after that, and soon we'll be able to add those together and get a more precise result. Okay, so I've come to the end of that, which is good, but let me just leave the conclusions up there and say that, you know, this is a really exciting experiment. It is really the opportunity now to look for, to really prove whether there is beyond, you know, physics beyond the standard model. And, you know, if we reach the precision that we expect to here, then in the next couple of years, you can see something really exciting coming out of Manchester, the universities that are contributing to this experiment, and the Fermilab itself. Okay, thank you. Thank you very much.
Thank you so much for that, Alex. That was super interesting. I didn't realize it had sort of so many consequences for all the different physics that we currently knew of. Just before we headed into the tour, I just wanted to, for everyone currently listening, I'm going to put a Google form into the chat, a link to one, and what you can do is you can enter questions there, or you can put them into the chat, and this can be ones you've thought of for the Q&A or for Alex based on the talk or while the tour is going on. Just either put questions in the Google form or straight into the chat, and then we can get around to answering them after the tour. But yeah, I hope everyone enjoyed that. I certainly did. So yeah, if we want to go on with the tour now, that'd be fantastic.
Let's jump on with the tour. Let me see if I can make this as big as I can. Can everyone see that? Is that all right if I do it just like that?
Yeah, that looks good.
Okay, so you saw at the beginning of the talk, I showed you where the MC1 building was. It had G-2, and then the MC2 building, which houses the Mu2E experiment. And so this here, for the start of this tour, this is the outside of the MC1 building. I won't start here. I'll swing around here just so we can see over this way. So this is the this building here is the booster. So as I said before, this is the third stage in the accelerator complex that then feeds the main injector recycler. And then this building here at the back is Wilson Hall. I can just quickly jump to the Wilson Hall virtual tour here, which there isn't much in here, right? But this is just the inside of Wilson Hall. When you go in, you can see that it's a fairly impressive building. But it's largely just offices. My office is somewhere up here on the 9th floor on this side. And this is that's where the Muon department sits. But there are some interesting things to see in here over this side, in this corner here. This room here is the control room for CMS that they monitor from Fermilab there, because Fermilab is very involved in CMS. And then there's another main control room here, which I think now is being purposed for June, but has housed things like Minos and the other experiments that were running at Fermilab before. All right, so this is Wilson Hall. Just wanted to jump through to there because it's another part of the tour. But then if I carry around this way, so again, we're outside MC1, the MC1 building now. This is the Mu2E building at the back here, right? So this is now where the Mu2E experiment will be housed once Muon G-2 finishes. And of course, as I said, we share that beam line. And so at some point, sadly, Muon G-2 will have to switch off. But luckily Mu2E will start, which hopefully means I'll still be in a job, because there'll still be an experiment to work on once the other one finishes. Okay. So before I jump into G-2, I'm just going to point out this thing here, because there's a sign on it. So the magnet is, like I said to you, it's a 1.45 Tesla magnet, and that's used to expose the muons to magnetic field, but also to radially focus the muons. And to get a magnet that large to that higher field, it has to be super cooled. It has to be a superconducting magnet. And so what we do is we flush the magnet with helium and liquid helium and liquid nitrogen. And this basically here is just a cooling tower which houses the liquid helium and liquid nitrogen. And there's a full cryogenic system which leads into this building at the back here, which then feeds the liquid helium and liquid nitrogen into the storage ring to keep the magnet super cooled. So let's jump into the building itself. So this here now is the experimental hall. We're at the top of what we call the high bay in the MC1 building of the Muon G-2 experiment. And you can see that you come in through this door over here, and then just come on these stairs here. And if you want to go down into the ring, you come down these stairs, right? And so before I jump into going around exactly what all of these parts here, I did have a look earlier, and there are some videos and bits and pieces here that it might be interesting for you to watch. So this ring, I didn't say this in the tour itself, but the Brookhaven measurement, as I said before, measured the anomalous moment last year, it was the previous measurement before this, is actually exactly the same ring. Okay, so the ring, it's the same ring that was repurposed. It was used for the Brookhaven experiment. It was repurposed for this experiment. But Brookhaven's out by New York, and Fermilab's out by Chicago, and so they had to get the ring from Brookhaven to Fermilab, and it was, you know, lots of questions of how do we do it? Do we helicopter it in, and you know, how do we do that without damaging the magnet? And in the end, it was decided that the quickest way to do it was by boat. So they took it out towards the East Coast, and they took it all the way down to the point where they hit a point where they could come in on the river, and then it came in on a barge, and it came all the way up the barge towards Illinois. And then once it reached Illinois and it was able to get on the road, there was a very, very slow drive from wherever it ported from, I can't remember where, overnight through to Fermilab. And I think this is a video of the night move itself. And so you can see that, if this decides to play, yeah. So you can see here that the ring was put, this was in 2013, was put on the back of this, on this truck, and it was taken through all these roads. And they actually closed basically the Illinois highway, one of the biggest motorways in Illinois, to make this move done for the night. And so I think I mean, I might be able to check the mark later. This might be the I-88, which leads into the main motorway that leads into it. But they had all these people here. You know, it was a big deal. It was all on kind of national news, and it came down these roads and it hit the motorway, and it really travelled overnight at 20 miles an hour all the way to the lab. We don't have to watch all of this. There's a lot of it just like traveling along the road, right? And it gets faster and faster. But you can tell that it was a really, really long process, and they had to do that to make sure, you know, the ring was stable and it wouldn't get damaged. And then once it was transported, oh no, that's not what I wanted to do. I wanted to close that. How do I close it? There we are. And then once it was just transported, it had to be brought into the ring itself. And so this is a video here which was a recording of when the ring was actually brought into the MC1 building. And so there was like, they had to build all the cryogenic systems and everything, get it ready for testing and commissioning. And so you can see that they had to build this structure. This was underneath, this was just a support structure here, and they had to build this scaffolding structure to get it in. This bit up here, you can see where my mouse is. This is where we were in the tour. This is that high bay part of the MC1 building. So they had to build this track and bring the ring across here, and then slowly lower it down. Whether they're going to do that, I think they craned it down, yeah. And you know, whilst they were doing that, they were getting everything else ready in the building. So in this corner here is where the cryogenic systems come in. You can see they've already been built here, right? And that's already been built on this part here. That's to supercool the magnet. And so the rest of the system then is built in this corner, and it feeds into here. But so we're slowly lowered onto the support structure here, and then the rest of it was all over God knows how long, but you know, bolted in, and then they started to build everything else around it. And you can see that they build the rest of the storage region, all of these support structures on the outside. The cryogenic system is then all the piping is starting to be put in. You know, so it's a long process, and this is years and years before the G-2 experiment even starts. You know, you can imagine how the amount of time and effort that went into planning this and coordinating it, and the amount of money that these things cost, and you know, not just but paying all the people to do it. And it's a huge enterprise, and it takes a long time. But it just goes to show that this kind of stuff is, one, really exciting, but also really worth the time, the money, and the effort that's put into it. And the fact that these things can go on for, you know, 20 odd years or more, if you take into account the data analysis that goes on afterwards, is really quite amazing. So that was that video. Okay, so I think that's the video of, and then there was an image here of, yeah, but this is just what we saw before. So this was the ring that was lowered in before everything was installed. So let me turn around and slowly show you the different parts. So if we're looking at the storage ring here, this back end here is what's called the M4, M5 beam line. And this is where the muons come from the accelerator campus into the ring itself. This is the injection point, all right? So if I click on this and go down here, you can see that this is the end of that beam line that comes. Remember, there was the delivery ring that I said that we circled 6 times to get rid of the protons and the pions and just to be left with muons. So that leads from there. And then this beam line is actually what the muons come down. And these are the quadrupoles, these focusing lenses, these electrostatic quadrupoles that focus the the muons through this beam, and they travel all the way through here, through these quads. And then behind here, just behind here, is that inflector magnet, the 1.7 meter long magnet I said that cancels the magnetic field of the storage ring and allows the muons to enter the storage ring itself, without being diverted away. Okay, so that's where the muons enter. If I go back up here, so then the muons enter at this point, just up here by the inflector, and then they come round, and you'll remember that we have electrostatic quadrupoles in the ring as well. I'll call them quads for now, because electrostatic quadrupoles is a bit of a mouthful. So we have 4 sets of quads. We have one here, we have one down in this corner, we have one at 7, 8 o'clock here, and then we have one at 10, 11 o'clock here. And you can actually see that these boxes here, these boxes are the power supplies and resistors for the quads themselves. So we have a set of plates here, a set of plates here, and then the same all the way around. So you can see that there's one here and one here. So those are the power supplies and resistors that feed the quadrupoles. Now, at that point, you remember that the muons will come in, but they're distorted from the orbit that we want them to be in. So when they reach the 90-degree position, here, this photo was taken a long time ago. So the system actually hasn't been installed at this point, but this is the point here where we have those 3 kicker magnets. And you can see the cables here that feed these kicker magnets. And in the experiment as it is now, down here in this corner, there's a big power supply that supplies 55,000 volts to a pulse forming system, which allows us to produce an electric pulse, a voltage at the specific time that we need it to, such that when we pass that voltage into those big dump resistors down here, it sends a current into the kicker plates that's in this magnet and produces a very on-off magnetic field that we need. You imagine how, remember I said that we have those 16 bunches, that happen one every 1.4 seconds, and we need to know those, really, really precisely. And so it's something like 150 nanoseconds that this magnet comes on and off 8 times in a second. Okay. And so that's quite a complicated system that then kicks the muons back onto the right storage region and on storage orbit. And once they're there, we have more quads here and here and that focus the beam vertically, and then we have the magnetic field that focuses the beam radially. Okay. So the muons, like I said, will travel around this, I think, about 500 times before they decay. And then when they decay to positrons, then they start to lose energy and they start to spiral inwards, to radially inwards towards the center. So let me go into the view from the center now. And you can see here that these boxes all the way around the edge, this 1, 2, these ones all here, these black ones, are all the calorimeters. And so there are, these ones still haven't been put in at this point here, but you can see these are the calorimeters, and there are 24 of them at equidistant positions all around the ring. And so at each point here, at some point, the muons will decay, the positrons will decay inwards. They'll come here. Somewhere inside this block here is those crystals, those lead fluoride crystals, which the positrons will hit, produce Cherenkov light, and then the silicon photomultipliers will detect that light and record the signal. And that gives us the time and energy distribution of the muons themselves. All right, so we have those 24 that exist all around the ring. We also have detectors, straw tracker detectors, which I mentioned briefly. Let me see if I can find one. Oh, this isn't, so just back here, you can see there's this block here. This is actually a garage which stores the trolley. Remember I said there was that long trolley with the magnetic probes that we used to put around the ring, which measured the center of the storage region. Well, that exists in this little garage, and then it has a magnetic thing, a mechanical thing that puts it backwards and forwards into the region under a vacuum. Obviously, the muons need to be they need to be stored on a vacuum. There can't be any air in there. So that's quite an enterprise in itself. And then here, so I don't know whether there isn't one here, but somewhere around here there should be some. There should be some straw trackers. Where are they? Maybe this is so long ago that they were in a different. Oh yeah, they're here. God, they don't exist here anymore. So here there are straw trackers, okay? And what we have, they don't actually exist here anymore. They exist at this point here, the 10 o'clock position. They exist at this point here. And what they basically are, they're long, they are exactly how they sound. They're straws with wires in between them, thin straws with wires in between them, with essentially pickups on the end the straws are filled with an argon ethane gas. And what happens is that when the positrons pass through them, the straw trackers will detect the positrons passing through that gas. A signal is passed through the wires, and it's detected out by the straw tracker detectors. And what that does is that gives us an ability to measure the beam distribution by extrapolating back from the decay point of the positrons to the center of the storage region. And it tells us what the beam's doing in terms of how it's moving throughout the storage region and over time, so that we can model the Betatron oscillations, that harmonic motion, that sloshing of the beam as it's going round. It also tells us if the beam's deciding to pitch up, and it gives us a really good cross-check and ability to measure all these systematic effects that we need to know really well to get to the measurement of the Muon G-2 as precise as we can get it. On top of that, we have another detector system called the fiber harps, which is like the straw trackers, but the straw trackers exist outside the ring. The fiber harps are inserted inside the ring. And it's the same concept, except that because they're put inside the ring in the storage region, they're a destructive measurement, because the positrons will hit them and then they can't keep orbiting around. So it ruins the measurement overall. So we can only use that for very additional cross checks if we need to measure something in particular and how the beam is moving, but we don't use that very, very often. All right. And then in terms of measuring the magnetic field, we have all of, the 387, I think it was, fixed probes that exist all on the top and underneath this region. And so when the muons are traveling around, they're constantly measuring, even if there's muons in there or not. If the magnet is on, it will measure the magnetic field. And then we use the trolley that runs through the center of this region here to map between what the fixed probes see and what the trolley sees, so we get a convoluted map of the magnetic field that the muons see inside the storage region. So we know exactly what muon is experiencing what magnetic field at any one time. Okay, generally, I think that's a lot of the information about how the experiment works. I did go through a lot of it when we were in the talk, but a lot of it's there. This black room here is actually a laser calibration system. For some reason, I've never been in this room, which is a massive failing of mine, because I have got the training to go in there. But when the positrons hit the calorimeters, there's a gain sag. We have a gain effect that we have to correct for. And so what the laser acts is basically a calibration system, and it allows us to determine a systematic uncertainty that comes from the gain effect from these calorimeters. And in here, there is a massive breadboard filled with mirrors. I mean, it's incredibly impressive, filled with mirrors and lasers, and yeah, it allows us to. It's a bit of a state-of-the-art system that allows us to measure that gain effect to a pretty high precision. It's quite something. But yeah, I think generally, in terms of me explaining what's in this room, that's largely it. So I'm happy to take questions now, as part of the tour. If you want, Fraser, I'm happy to take some.
Yeah, I mean, yeah, we can get a couple of questions in before the Q&A. So I guess if anyone has any specific questions, I'll check the Google form, but if anyone has any specific questions they'd just like to ask out loud, you could just unmute yourselves and ask Alex, probably at this point specifically about the tour or about the Muon.
Yeah, I mean, about the presentation of the tour, anything.
So anything to do with that, and I'll just give me 2 seconds and I'll check the Google form just to see if anyone's anything in there. And if you don't want to unmute yourself, you can always ask it in the chat as well. I know I at least have a couple of questions as well, so I'll just find what I've written down. And you can also use the raise hand function on Zoom if you want us to unmute you, but you can just unmute yourselves.
I did have a question about the first order correction for the G2 factor. So the first order correction was the photon, the virtual photon vertex.
The Schwinger term, yeah. You're talking about, where are we? This photon correction here.
Yeah, that one. So I'm having a hard time understanding why the photon would have an effect on the magnetic moment measurement, because does a photon have a magnetic moment?
The photon doesn't have a magnetic moment, no. But what happens is that this is a virtual process in the sense that the electron or the muon that interacts with this photon, without that virtual photon there, is just a tree level process. Okay, so imagine we want to measure the coupling constant of that interaction there, the point where the photon and the electron meet. Now, what happens is that because these virtual processes can happen, the incoming and outgoing electron can exchange these virtual particles. All right, that's just a virtual process that happens all the time. But what that does is, you can imagine it in the sense that it will screen the coupling that the external photon and the external electron will see, and so it changes the value of the coupling slightly, because it's almost like it's shielding. This obviously isn't physically what happens, but you just have to imagine it in that way. It's almost like it's shielding that coupling constant and changing the value slightly. And these relative corrections are a manifestation of something called renormalization. I don't know if you've done renormalization before, but it's the process by which you have to take bare quantities like masses and couplings and charges, and then incorporate these higher order effects such that they adjust these values to what their physical values are. And so it's not necessarily just a photon that will interact, that will be exchanged there, but the photon itself could have a loop. So that photon in the middle could have an electron positron loop, which would be, the virtual photon would have an electron positron loop inside it, and then that would change that value even more.
Okay. Yeah, makes sense. Thank you.
We've had a question through the Google form, and I guess this is not so much about the Muon G-2 apparatus, but it was kind of like what sort of your daily timetable is like, Alex, and what you're doing within the obviously I know it'd be very changed, but in an ideal world, in a normal world, what would it be like? And maybe help to get an interest and see how it's been affected.
Yeah, so this year, as you could probably imagine, it's changed quite a lot. So you said at the beginning that I was the run coordinator for the experiment. So that was actually at the beginning of this year, up until February or March time. And the run coordinators have the onerous job, I would say, of making sure that the experiment's running 24/7. And when you run coordinator, that means that the buck kind of ends with you if there are any problems. And so when I was over in Chicago, you don't really have a working day, because you can get called up at 1 o'clock, 2 o'clock, 3 o'clock, 4. These experiments run overnight, and so someone will inevitably stop working. Everything works fine during the day, and everything stops working at 3 o'clock in the morning, and then you get a call, and sometimes you have to go into the lab to fix things. So at that point, that's that can be quite that's a difficult day-to-day running, but you learn a lot. After that, I moved on to being the operations manager for the experiment, which was then more kind of oversight, but I went less from working on the hardware and the experiment itself and making sure it was running, to attending meetings at the lab, and everything, and to what money we're spending this time, to how we're going to get back up and running during COVID. So that was quite stressful in itself, but that was more of a, I'd say it was more of it wasn't a 9-to-5 job, because then I had my own research responsibilities that I did around that, and so I worked generally more around that. But at the moment, now that I'm away from the lab, I don't have those roles, and so I've taken on an analysis role. And in general, my day is how I want to set it. I love what I do. It's really interesting, and I genuinely do love what I do. It doesn't really ever feel like work, and so I work because I work hard because I want to, because it really interests me. And so, generally I'll work from in the morning until sometime late in the evening, and you have to take into account time difference, because the experiment's in Chicago, and so it will run a lot later at night, if there are meetings going on, or you have to speak to someone on the other side of the world. But yeah, I mean, that's the way it usually works. And if sometimes you need to be on shift, when the experiment's running, people have to take shifts in turns to make sure everything's ticking over. And so last week I was on shift, and next week I'm on shift from 2 till 10 p.m. every day of the week. So yeah, it varies, but you know, it's really interesting stuff. And now my main goals are focusing on some data analysis for G-2 for the next year. That's going to be what I'm doing.
Yeah, it certainly sounds fascinating. And then I guess I just had one sort of question. It might be, don't know how difficult it will be to answer this one, but I was kind of thinking, so obviously the goal is for looking for new physics.
Yeah.
Can that new physics, so if you did detect more than 5 sigma deviation, can that new physics maybe come as well from, you know, processes used to make up the beam? You know, you were talking about all the different stages that go into actually creating the muons. How do you sort of know where that difference in the standard model is? It might not
exactly
be from the anomalous moment and something.
It's a great question. So you're totally right in that, you know, we have so many effects that, you know, that go on in the experiment that we have to account for. The beam's moving all over the place. We have to take into account things like temperature in the hall. The temperature will affect how the magnet works. You know, you can imagine all kind of systematic effects that we need to make sure we know and understand. But what we do is we spend years and years finding all of these effects and testing them, and making sure that we know them to a high enough precision that they can be accounted for properly, but also that they don't, you know, there are ways to check whether they're entering the beam dynamics that we're seeing. And so, for example, if you look at, a good example would be if I go to the frequency spectrum that I showed before. So, for example, where is it? Here. So this frequency spectrum shows you that we're picking up other frequencies other than the precession frequency. And so what we do, maybe should have shown this in here, but once we incorporate those into this effect, into this fit function, all of these frequency spectrums will disappear, and you end up with just a flat line at the bottom. And then that just shows you that you're not having anything from the beam dynamics bleed in here that is then affecting the value of the measurement that we want. All right. And so, you know, it is exceptionally tricky. It's exceptionally tricky to account for all of these things, but it is now taken about 3 years, and we believe that we really have got all of these down to the understanding that we need them to be.
Yeah, that's absolutely amazing. I mean, yes, yeah, as you said, the vast, 17 parameters sort of speaks for itself, or more. That many parameters in the function. Okay, I think we've got 2 of the panelists. So I know Terry Wyatt might be running a little bit late, so we can get the Q&A section. Is that up now?
Okay, shall I stop sharing then?
Yeah, that would be fantastic.
Thank you, guys.
And I will just work out how to pin everybody. So I think we have Mark and Justin in at the moment. So what I'll do is I'll just do like I did with Alex. I'll do a brief introduction for you two. I'll share my screen, and then we can get the Q&A portion underway. So one of our Q&A panelists today is Professor Justin Evans. He's a senior lecturer in physics and a member of the particle physics group at the University of Manchester. He specializes in the study of neutrino physics and has been part of the MINOS experiment, or MINOS, based at Fermilab, which is another one of the experiments on campus. And he's lead author on the world's most precise measurement of the first atmospheric neutrino mass splitting. So he's very much involved with the neutrino sides of things. And then we have Professor Mark Lancaster, who's again a professor of particle physics at the University of Manchester. And he worked at the Fermilab Betatron collider and was part of the CDF experiment. And he's also the co-spokesperson of the Fermilab Muon g-2 experiment as of 2018. So now I'll stop sharing and I will hand back over to Mark and Justin. And if you guys want to add anything to those introductions and maybe give a brief sort of idea of what your research with Fermilab was, a brief summary, or on what you're doing just now, that'd be fantastic. But yeah, thank you for being here.
Yeah, thanks. Well, yeah, go on, Justin. Go on.
No, don't think it matters what order we go. Yeah, no, yeah, thanks for the introductions. Yeah, so I work on the neutrino program at Fermilab. So I've worked on the neutrino program there since I started my PhD, which was that 2004, I think. So yeah, so the Muons project was a neutrino experiment that I did my PhD thesis on. So that was one where we fired a beam of neutrinos from Chicago up to northern Minnesota to a tiny little mining town called Sudan, where we had a big ion detector half a mile underground. And so yeah, so we made sort of precision measurements of neutrino oscillation parameters there. That switched off in 2014, I think, and it's been dismantled. So now I work on two Fermilab experiments. One is the microboon experiment, which is a liquid argon time projection chamber that's taking data at the moment. That's what we call a short baseline experiment, which means it literally means we don't send the neutrinos very far. The baseline is short rather than long. So we just send the neutrinos 1 kilometer, and we look for very fast neutrino oscillations, which can only exist if there's a fourth type of neutrino, which we call a sterile neutrino. We call it sterile because it doesn't interact with anything, otherwise we'd have seen it already. So that's one of the experiments. The other experiment I work on is the Dune experiment that Fraser mentioned. So that's under construction, and that will be a long baseline experiment. So we'll be sending neutrinos 1,300 kilometers from Fermilab to the Homestake gold mine in the Black Hills in South Dakota. And yes, as Fraser said, that's to look for CP violations, so an asymmetry between matter and antimatter in neutrinos.
Fantastic, thank you, Justin. And Mark?
Yeah, I'm a bit ancient. I think I'm probably the person who's worked at Fermilab the longest, I think, in the whole of the UK, actually. I first went to Fermilab in about 1995. I got there about 3 months after they discovered the top quark at Fermilab, and so therefore I missed getting my name on that paper by about 3 weeks, which was a bit annoying. And I've been working there on and off basically for about the last 25 years. I worked on this experiment you talked about, the Tevatron, which was basically a mini LHC. It had a beam energy about 10 times lower than what the LHC now has, but it obviously discovered the top quark, very, very nearly discovered the Higgs boson. It probably would have done had it run for another couple of years. The crucial thing that it did was that in order to build that accelerator, and as Alex said, if you need a high magnetic field, you have to have superconducting materials. You have to have a superconducting magnet. So to have the high energies that the Tevatron needed, they had to essentially invent superconducting magnets. So they were essentially invented in the early 80s at Fermilab by a sort of process of trial and error largely. And then CERN completely stole that design and built the LHC on the basis of it. But the Tevatron was the real pioneer in superconducting technology. So that ran until 2010. I then had a brief excursion where I worked in Japan for a couple of years on a Muon experiment. So I sort of decided in 2010 that I didn't want to go to CERN and join the LHC because the physics was, although it was at a higher energy, was very similar to what I'd already been doing for 15 years. So I decided to do something completely different in order to, tax my brain and work, look at something new. So I decided to move into Muons because it was an emerging area of research, and I started that in Japan, but gradually it became clear that the best place to do that was, again, Fermilab. So having sort of stopped working at Fermilab for a couple of years, I found myself back there in 2011, 12, and I've sort of been there on and off ever since, really, working on the G-2 experiment, and also hopefully we'll be taking data soon with another experiment beyond that, which I think Alex showed a picture of, this Mu2E experiment that will start taking data in 2 or 3 years' time. It's being built at the moment. So yeah, so I've had a long history with Fermilab, and it's changed a lot over the years, but it's still a great place to do science.
Fantastic. Yeah, sounds very interesting. So we've had a question come through, and this is a bit of a general question. You can probably all answer it for your respective experiments. But someone's asked sort of what's the worst issue you've ever come across? So I know for Alex, this would be on Muon G-2, while you were the run manager. What's sort of the worst issue you've come across, while the experiment's been running, and how have you resolved that?
You mean other than nearly losing my hand to a brick?
Yeah.
I would, well, go on. I would say of experiments, it tends not to be the physics or the experiments, which
it's the people.
It's the people, because these are big sociological experiments of hundreds of people and lots of egos, obviously most of them male, right? And there's a lot of bureaucracy, and particularly in the US, there's a lot of bureaucracy. So actually most of my pain has been dealing with funding agencies being constantly reviewed. So I've been doing particle physics for God knows like 30 odd years. And I think it used to be that if somebody gave you a pound to spend on your research, you probably had to spend 20 pence, not justifying it, but writing reports of what you've done. I think now for every pound you get given, you spend a pound working, to write reports and being reviewed. So almost you're being reviewed as much as you're actually doing the science, because they want to make sure that they're not wasting any money, because there was a big collider in the early 90s that got cancelled in the US, that having already spent, $1 billion or whatever. So after that, they got very cautious about spending lots of money. So now the review process for all of these experiments, and Justin, I'm sure will echo this with June, which is a huge, multi-billion-dollar project, is enormous. And after it, that can be quite soul-destroying, actually. But that's mostly my job. You see, Alex tends not to deal with that sort of stuff. Well, he dealt with the bureaucrats. The brick hitting the magnet cost me 9 months of my life, probably.
Yeah, I would say is other than authenticating passwords is another one that really wastes a lot of your time. But the people is I mean, in day to day, right? Generally, people that you work with are great, and the experiment you work on is really, really fun. But sometimes things go wrong, or people they have opinions about the way things should work, and especially if you get to the point where you're responsible for something, sometimes you have to deal with that incident or deal with that person, and you have to make a decision that someone's not going to like, and that can be difficult. Because people think that things should be done a certain way. But yeah, I mean, luckily from Mark, like Mark said, I've been up, well, until I did it a bit this year, but I haven't been so much I haven't had 30 years of bureaucracy.
There's also some things where you do something and you're supposed to produce, say, some apparatus, or something is supposed to do X, and you start building it and it looks like it's never going to do X because it doesn't work. And you think that, oh my God, I'm never going to get this thing to work. And I've just spent £200,000 on this and it's not going to work. Oh God, we had the wrong design. And you can begin to sort of worry or panic, thinking you'll never get something to work. And sometimes things go wrong. On this experiment, the Deviation as an example, we had a detector which was detecting charged particles, and we'd been running it for about a year. And then every day we looked at it, it looked like its efficiency of detecting particles was going lower and lower, such that it looked like within another year, and it had to run for 10 years, that it was going to go to zero and be totally useless. And it had taken 8 years to build. And so everybody started panicking and going, oh my God, why is this detector? It was essentially just decaying in front of our eyes and stopping working. And we did loads of things to try and investigate what that was. And then by accident, these things have gases going through them. We actually introduced air or oxygen accidentally into it while we were trying to work out what was going on. And that fixed it. So that was a guru bit of chemistry that nobody ever knew of, polymers coating wires at high voltages, where if you flow oxygen through it, for some reason, it cleans the wires. And then miraculously, this thing started working again. And so that was a sort of example of where there were hundreds of people panicking, going, oh my God, we've just wasted 15 years of our lives building this and trying to build this huge experiment, and it not working. But in the end, it did work. So you need a bit of luck as well. The LHC didn't have any luck when its magnets blew up. Within 5 days of started taking data in 2008, and that was just down to just a very tiny mishap in soldering superconducting cables. It was a tiny thing, but it caused the whole magnet to blow up. So those things definitely, and you can kill somebody, of course, right?
That is true, yeah.
So
the other thing, sorry, Justin, before I do want to get, but the other thing that just jumped into my head, and it pertains to what you said, Fraser, at your last question, is gossip. And when I say gossip, I mean, we have these experiments that run close to near discoveries and can change the way we understand things. And generally, you have a lot of people, and especially a lot of theorists, working all over the world, or not necessarily theorists, but deciding that they've come up with new ideas why you've done something wrong, or why something you've measured isn't something you've measured. And there was about, I can't remember how long ago now, maybe Mark remembers, it was about 3 years ago now, but a paper came out with G-2 from some Japanese scientists that basically had said they proved that there was no discrepancy because we'd forgotten to incorporate general relativity effects. I can't even remember what it was, but I was a PhD student at the time, and I worked, it was literally 3 hours one morning, and I redid their calculation, their paper, and it was so wrong. I mean, it was so wrong, this paper. But because it then goes on the archive, I mean, I don't know how much you guys know the archive, but it's so basically a public repository where you can upload these papers. The papers hit the archive, and suddenly, this thing then is rampant around the physics community that we've done something wrong. And that nearly ended up taking 6 years of my life. I mean, I did that. I remember doing that calculation in the morning and just taking a picture of it, and said I was in Liverpool at the time. Must have been 4 years ago. And before I knew it, this picture of the board in my office in Liverpool was being shown in presentations all over. Like it was in Italy, and it was in the US, because it was nonsense. And if those people if they'd done their work properly and hadn't checked their work, I mean, it was so wrong. So wrong. Sorry, Justin, go on.
Right. No, I can't disagree with any of that. Working in big collaborations, people are, working with people is always hard. Managing people is just hard. And yes, as Mark says, the level of bureaucracy and review we have to get through to get these projects off the ground can be quite demoralizing at times. You have to sort of steel yourself and remember there's physics at the end of it. So Dune is a $2 billion project, basically. And so we're working with the Department of Energy, which is the main funder in the US of high energy physics. And pretty much all we're ever doing is having a review on some subsystem of a detector every 2 months. So I almost can't remember the last time I did physics on Dune. I'm at the moment just doing project management pretty much. So, those can be very difficult. It's a very difficult part of the project to motivate yourself to get through. But then there is physics at the end, so you have to keep your eye on the light at the end of that tunnel. I also work on microboom. That's why I work on 2 projects. So that I've got one where I'm trying to where I'm doing the boring, tedious project management, but one where I'm actually analyzing data, which is the fun stuff. In terms of the worst sort of potentially mission critical thing that happened on an experiment, so Minos, which is a neutrino experiment, so I did my PhD and my postdoc on. So that's at the bottom of a disused iron mine in northern Minnesota, so it's about half a mile down, and so there's a half-mile vertical mine shaft. One night that mine shaft caught fire, and putting out a fire that's halfway down a half-mile long mine shaft is not easy. And so the Minnesota fire crew came, and all they could do was pump foam down it for about 48 hours until the mine shaft filled up and the fire stopped. And of course, at the bottom of that mine shaft, your detector is in a 20-meter high aircraft hangar-sized cavern, which is gradually filling up with foam for 2 days, and you have no idea if it's surviving. And so we just had to wait for 2 days whilst they filled it up with foam, and then another week while they made sure it had gone out and let the foam clear enough that someone could go down, and then send us up photographs of our detector hall full of foam. Unfortunately, the foam had gone along the detector hall and got to the front face of the detector and hit the front face of the detector, and then had stopped. And so the electronics running the detector, which were about 3 or 4 meters further away, were fine. If a foam had gone that extra 4 meters, we wouldn't have switched this thing back on again. but it stopped just in time. So that was probably the scariest moment of, is our detector dead?
Yes.
Yeah.
Do you want that, Justin? Fire in a Mine Shaft is a good name for an album. You should use that.
You should do, yes.
The next question we've got is, again, pertains to pretty much any experiment. And it is, you were talking about data analysis, Alex, which is what you're doing right now. But the person's asking, have there been any recent developments that have allowed you to analyze data sort of live as it's coming from the experiment, rather than sort of doing it all after the fact, as you're saying, you're doing sort of data from past runs? And I guess,
yeah, so we do monitor data live as it comes through. So we have different data streams that come off the experiment. We have an online system, and we have what we call a nearline system, and we have an offline system. And the offline system is really the full data package. So everything that we recorded is stored, and that's sent off to tape to be recorded, and is then analysed by the data analysts over a long-term period. The nearline data is a kind of a small subset of that, which is the same idea, but it allows us to do specific. So, for example, if we want to know where the beam is in the g-2 experiment at a certain time, we can use the nearline data to run a quick analysis over that small amount of data, which will give us an idea. But the online is really real time. So we have a data acquisition system which tells us at any particular point, and a data quality is called a DQM, a data quality monitoring system, which we can see the muons and the positrons as they're being recorded. We can see the muons as they're coming in past the detector at the inflector end. We call it the IBMS. It's like an initial beam detector. And so we see all these pages. And when you're on shift, that's the point of being on shift, is that you have all of these windows up, and there's all of these things that are blipping, and you can see. I mean, if the accelerator, it's such a shame. I've just had an email to say that the accelerator is delayed again by another day. Otherwise, I would have shared my screen and showed you the thing running. But you can, you see all of that stuff, and then it's a clever system whereby if something goes wrong, an alarm will go off, and you're able to go in and fix something. I mean, that's how it works generally on all experiments, I think. But Mark and Justin.
Well, yeah, I mean, it's sort of changed over the years. I mean, to put it in context, g-2 writes data to disk, or tape actually, at about 1 terabyte an hour. So that's the sort of rate of data, and that's fairly typical for most experiments, that you're writing several terabytes an hour. And over the years, things have changed. So at the collider experiments like the LHC, the amount of data, because these collisions produce so many particles, but if you were to write all that data that actually comes out of the detector, you would be writing probably petabytes of data an hour. So they actually, in real time, have to throw away 99.99% of their data in a fraction of a second, right? In a few microseconds, they have to throw the data away. And that's quite scary. So you put that into dedicated electronics. It's typically these things called field programmable gate arrays, FPGAs. And they make very quick but rather simple decisions. And you have to program that, and you go, okay, does this event look like a Higgs boson? Yes, let's keep it. Does it not look like a Higgs boson? Let's throw it away. If you screw that up, you lose all your data. So that's quite scary. And so a lot of experiments now, because the processing power in these online devices keeps going up and up and up. So many experiments are now going, let's not throw anything away. Let's try and, on CPUs, GPUs, and FPGAs, somehow analyze the data quickly. By quickly, I mean on the time scale of a few seconds or minutes, right, or hours potentially. And let's then write that to disk. And so many experiments, I think June's probably going to do that, right? Typically digitize everything and then look at it. We digitize everything and write everything out. One of the LHC experiments is looking at moving in that direction. So it has changed over the years. So these devices, which are very quick, but often quite difficult to program. You can't just, write Python or C++ on them. You have to write in a dedicated language, VHDL, to program it. But they're incredibly quick. They can do operations every, of the order of every few nanoseconds, they will do an operation. They tend to be very simple operations. But if you add them all together, you can do quite powerful selections. So it's, yeah.
Yeah, I mean, historically, too much data is a problem a neutrino physicist can only dream of, because you're usually dealing with, you know, about 3 events a day or something. So, you know, I mean, you know, go back 10 years and I wouldn't even be thinking about this, but we've dealing with the liquid argon time projection chambers, we're now actually hitting sort of similar data rates as those, you know, that Mark's talking about, and the data rates that the LHC experiments are talking about. We have hundreds of thousands of channels reading out every few seconds. And again, yeah, it's all about this triggering that Mark was talking about. For us, it's not actually so much the neutrinos that we fire from Fermilab, because those still only happen, you know, 1 or 2 a day in the detector. So that's fairly easy to catch. The thing we want to do with Dune is to be able to detect the neutrinos from a supernova. That's the really interesting sort of big data problem, because we expect that, you know, in the 30, 40 years that we're running Dune for, somewhere in the galaxy there will probably be 1 supernova in the time that Dune's running. And depending on how close it is, you could see 1,000, 3,000 neutrino interactions in the detector. And we've got 1 chance to do that in the entire 30-year running of the detector. And so what we have to be doing is completely online, underground, triggering on, have we seen a signal that looks like 1,000 low energy electron neutrinos all coming from the same point in space? We're trying to do that problem, and that's the really hard problem, where all of these things Mark is talking about, FPGAs, GPUs, are going to be used to solve this. On top of that, we've got the problem of getting the data from underground to the surface. You know, you've got to go up a mile along a thin cable. So all of this has got to be done underground, bottom of a mine shaft. You've got to make that decision. Am I throwing away the past 10 minutes of my data, or am I actually storing 10 minutes of data and spending the next day piping it up to the surface because it looks like a supernova? So that's, yeah, that's the sort of problems we're trying to solve.
Yeah, no, it's really.
I mean, also to add to that, famously, I mean, the last supernova was it 1988, and IMB was a neutrino detector then, and their DAC was off for the, you know, the 3 hours that the supernova hit the detector. They were just doing some routine maintenance and completely missed it.
Yeah, not ideal.
That was a bit unlucky.
Yeah, it's a nightmare scenario, I think.
Justin makes a good point, though, in the sense that you know, timing for these things is really difficult. You know, it doesn't matter what experiment you're on. You know, if the g-2, for example, we have that bunch structure, and so if we want to see that data in real time, not only does everything at the experiment have to work at exactly the time that we need it to, so we know that we're detecting and storing things and measuring them at the same time, but you know, we then have to have a data acquisition system that can trigger all that stuff at the time we need it to. And when you're talking about hundreds of nanoseconds or smaller time windows, it's, you know, that it takes a lot of time and effort to get that right. And it's an area of physics that's really interesting, but actually, you know, not a lot of people see until they get to the point where they're working on an experiment, and have to understand how all these things work. It's really fascinating.
Yeah. The next question sort of it does relate quite a lot to Dune and a supernova, and I guess it's kind of a big question as well. So it's sort of like, do you see the future? You know, you've got particle physics, multi-messenger astronomy now, and astroparticle physics becoming more. Do you think that newer experiments, these big sort of money experiments, will be moving more towards sort of observing sort of astrophysical events rather than creating something in lab? So for example, you've got Dune as an example of that. So yeah, just sort of, is there a shift away now from straight particle physics towards sort of more astrophysics, particle?
I mean, yeah, I wouldn't say a shift away. It is certainly true that multi-messenger physics is a very exciting new area of physics. You know, with IceCube, you know, in the last 5 years, seeing the first high energy neutrinos from outside our solar system, that's opened up an entire new bunch of physics. So it's very clear that there is going to be an awful lot more interest, an awful lot more funding and activity going into these astrophysical experiments. That's not to say we're going to stop doing the stuff in the lab, because if you want to, I mean, what you can do with these astrophysical experiments is you can work out you can find out things about astrophysical bodies and how they work, right? And you can find out things about particle physics that way, but you're much more using particle physics as a tool to work out how astrophysics works. If you want to really understand the nature of the particle, it really helps to have a nice controlled source of particles that you made in a lab. It's very, you know, it's very hard for me to study a neutrino using neutrinos that have come from, you know, the Andromeda galaxy somewhere. So I don't know how many neutrinos the Andromeda galaxy were producing. I can definitely tell you things, you know, do interesting science, but you really need to be able to control the source of your particles if you want to do precision particle physics. So that lab-based particle physics, it isn't going anywhere, I think.
Yeah, because I mean, that's also true. If you look at the dark matter experiments and the early solar neutrino experiments, they were very reliant on the models of what was going on in the sun or various other things. And so you always get hit by these models of what's producing your particles. But it's certainly the case, I think, that, I mean, you know, a big area of research is people trying to understand dark energy in the lab by looking at sort of atom interferometry type experiments. I mean, they're potentially going to have an experiment there in the Minos hall at Fermilab, where they have an interferometer going down, you know, a couple of 100 meters or whatever, and looking for axions, these mythical particles which solve the problem in the strong interaction, which nobody's ever seen. Or people talk about dark photons, which are essentially dark, you know, they don't interact with normal matter in a normal way. They're very light Z bosons, if you like, sort of electron volts mass Z boson. So there's a push as well as people looking at very high energies, which obviously the LHC does an incredible job of, is also looking at very low energies. You know, Justin mentioned sterile neutrinos, but there's axions, dark photons, all sorts of things, which tend to be very low mass objects. But if you have enough of them, then they have, you know, clearly they have big cosmological implications. So there's certainly a push in that direction to move lower in mass. It used to be that all we did was build the next collider to go higher in mass, but people have begun to realize, I think, that there's also interesting stuff at the low end, right, if you have it in the right abundance. So that's a push as well.
Yeah, and from a phenomenological standpoint, that's really interesting, right? Because we, you know, it's like what I was saying in the talk, we understand particle physics at high energies very well in the sense that we can calculate all of these, you know, effects perturbatively for QED, and things like low energy hadron physics, we don't have those calculations. And so then this whole area of physics comes about, which was very popular, you know, I don't know how, decades ago now, where people were modeling low energy hadronic physics, but it kind of fell out of fashion. And now it's getting to the point where we're pushing the energy boundaries higher and higher, and people are now looking back. We're not finding anything there, and people are looking back and thinking, well, you know, we don't fully understand this sector of QCD. We can't really predict what goes on at low energies very well. And you know, those low energy quark models, the parton models, you know, there could be something there, and that's where these things like axions and stuff start to come into play.
Right, yeah, I didn't actually know that. That's completely new to me. The next one is sort of related to looking to the future, but it's if you know anything about future plans at Fermilab. Obviously, I know you're all involved in it to some degree, but what are sort of the most exciting things we can expect to see from Fermilab in the next couple of decades or further into the future?
I mean, I wish I knew the answer to that, actually, because both CERN and Fermilab are both struggling with, you know, the LHC will take data until, you know, let's say 2030, 2040, 2040 probably, right? It'll take data till 2040. June will probably take data until 2040, something like that, I guess, right? And so there's a big horizon coming at 2040 where, in order to have something working in 2040, you've got to start planning it now, because it takes 20 years to get the money and build these things. And there's a lot of debate about exactly what that is. I think in Europe at CERN, they want to build a huge 100-kilometer collider, which will take a long time to dig that tunnel and build, and various other things. Fermilab, I think, if I was to guess, the direction they will go in is they tend to be much more aligned with what we were talking about before about the sort of astrophysical and cosmological connections. And so, and understanding dark energy and, you know, quantum sensors and quite subtle quantum mechanical effects. So they, if I was to place a guess, I would imagine Fermilab will go down that route then, but there is no clear, I would say there's no clear decision yet. Well, there are decisions, there are aspirations, but I think it also depends what everybody finds. I mean, if we start finding sterile neutrinos, or the LHC starts seeing new particles at, you know, 11 TeV or some mass scale like that, that completely changes everything. Or if g-2 finds something which maybe is confirmed in another experiment, and then it turns out that all the interesting new physics is at a GeV or something, then that completely changes the future. So that's the beauty of what we do, is that we don't really know, and you have to have a guess. But when those guesses cost $10 billion, it's it's difficult. So my view has always been to try and build many, you know, smaller experiments which are cheaper and somehow have a bit more of a scattergun approach, as opposed to putting all your eggs in one basket. But equally, you have to keep people, you have to keep the labs going, and they have to have a big project. And so that's also a motivation. But it's a very difficult. It's going to be for your generation to solve that and work on these things, really, because come 2040, I don't think I will be doing particle physics. So
come 2025, I think.
Yeah, I'll be on the golf course.
Yeah, it is going to be a big problem for Fermilab to come up with that vision. As Mark says, you know, we're coming at the point where we don't know what we're going to find in the next 10 years, and that's what will inform us. So, you know, we're not even ready to make that decision yet. It's very clear, you know, Dune is the next big thing for Fermilab from now until 2040, something like that. So that is what's keeping Fermilab busy, and so that will be, you know, the big, you know, sort of the big ticket, exciting results in that 2030, 2040 timescale. It will be from Dune.
I mean, it probably just means there's going to be a gap, isn't there? Because by the time you see something, then have to do something, there'll be a gap. And that didn't used to be the case 20 or 30 years ago, because you could build an experiment in 5 years, and go from, you know, having the idea to it running in 10 years or something. Now you can't do anything in less than 20 years is the issue. So you have to have the idea now for it to be going in 2040. But I think the likelihood is we'll wait to see what the results of all these experiments are, and then a decision will be made at Fermilab and in Europe. And it may be that Fermilab, you know, already does this. It will have to join forces with CERN or vice versa. So CERN's helping a lot with the neutrino project at Fermilab, and Fermilab's helping a lot with the LHC upgrade project at CERN. And there are big discussions between those two labs, and the same project won't be at both labs. That's for sure, right? That's definitely the case.
There's a long-term spiteful element in the sense of it, right? In the sense that the longer that these experiments around the world run, and we don't find anything, the longer, the more parameter space we lose to, you know, these models have existed for years and years. And you take supersymmetry, for example, and the longer the LHC runs and doesn't find anything, the more it reduces the parameter space that's left to find something. And so, you know, as much as you could say that's a motivation to build a bigger, more expensive experiment, it's also a motivation to say, well, the chances of finding something are getting slimmer and slimmer. And some models, yeah, there are lots of models that have been excluded already. In g-2, for example, if you go back 10 years, you could still probably have a number of SUSY models that could explain g-2, but as the LHC's carried on, you know, that parameter space is gone. Because they've not found it. And so it's a really difficult balance. You kind of have to make a decision based on something that you hope to happen in the future, and maybe it does or doesn't happen. But if you wait, sometimes you can pin something on. You know, we could pin. Mark and I have this discussion every other week when we get drunk. We decide what we're going to do next, and you know, we always, but it hinges on what result we get from g-2, and we just don't know. It's really hard.
But I think it's also the case in particle physics. You know, I've been doing it a while. The path has always been fairly clear, because it started off, the standard model had its infancy, and it was like, okay, we've got to discover the top quark. We know it's there. The theory tells us it's there. Let's find it. They find it. Prior to that, it was, well, we know the W and Z bosons are there. Let's go and find it. So they do that. Then after that, it was, some of it was neutrinos. Well, they knew the Higgs boson existed. So it was, well, or did or didn't, but, you know, largely inferred that the Higgs boson should exist. It's like, right, we have to build an accelerator which will find the Higgs boson, which was the LHC. Neutrinos are similar now. We have to do precise measurements of neutrino oscillations, which is dictated why June is being built. But beyond that, we're in a very different scenario then, because there isn't a clear path. And previously there always was a clear path, and it was like, right, we are going to build this. Right, let's do it. Whereas we're not in that situation now, which is the first time particle physics has been in that situation since the 50s.
Exciting time then to be doing physics, I suppose.
In some ways it's exciting. In some ways you could also, you know, the whole field could be overtaken by something else, right? If you stand still for too long, somebody else will do something, you know. When I did my PhD, cosmology didn't exist as a subject, basically, and now it's a huge area of research, right? But again, that's getting expensive, and, you know, they're now coming to multi-year, you know, experiments and timescales. But yeah, you can't stand still, but equally, if you don't know what the direction is, it's very difficult to go running off in a certain direction.
The next question we've just had from somebody is sort of, what advice would you give to a student who's looking to maybe work on an experiment, one of these sort of experiments? I know it's a very general question, but I think they're just interested, perhaps.
Just try it out, I think. You know, I mean, yeah. People often ask questions along the lines of, you know, which experiment should I work on? What direction should I go in? And, you know, that's an unanswerable question because the answer doesn't matter. You know, do an MPhys project in particle physics, get a feeling for what it's like working with the research groups, right? And it really doesn't matter what you do. Okay, if you end up doing a research project with Harry Wyatt on the top quark, it's not going to stop you doing a PhD in neutrino physics if you want to go in that direction. It really doesn't matter. And then, yeah, after, you know, as you're doing your MPhys project, get to know the researchers in these groups, so that you've got an idea of what the PhD opportunities are out there, and then apply for PhDs. So, you know, I mean, that really is the best way in. You know, read about the subject, know what's going on, so that you can have intelligent conversations with the professors you meet in the coffee area, and then just apply for everything. Don't narrow yourself down to one subfield. Don't narrow yourself down to one institution. You know, go anywhere in the UK that will give you an offer in particle physics. So just, yeah, keep your horizons open, basically, and go for it. I think is probably the advice.
Yeah, I totally agree with that. And as well, it's also the case, because experimental particle physics is an expensive endeavor. You know, there are 50 physics departments in the UK, but only, I don't know, what's the number, 15, 20, 15 are doing experimental particle physics. And all of those are world-leading places by definition, because to survive in that sort of ecosystem, you have to be good, right? And so they're all good. So, and the skills that you learn doing neutrinos or LHC, they're not actually that dissimilar. A lot of it is, how do you select and analyze data, or see a signal amidst a lot of background and write clever algorithms to mine the data? And I mean, a lot of the skills are the same. So yeah, as Justin said, you should not really just I mean, I had no idea what I wanted to do. And I thought I wanted to work on one experiment for my PhD project, and I got taken to the pub by some people. They got me very drunk, and I ended up working on something else for 7 years. And then I didn't quite know what I was going to do. And they said, why don't you go to Fermilab? I went, where's that? And they, you know, you get sent to, I went there, and I've been there, you know. So there's some of it is a random stochastic walk of what you end up doing. And you should just do what you think is interesting. And if you're enjoying it, carry on doing it. If you're not, do something else.
Yeah, I'd say, exposure and who you associate yourself with, and that kind of interpersonal contact is really important too. I mean, I now work on, you know, 2 experiments at Fermilab, and I did a theoretical physics PhD, right? I hadn't done any experimental physics up until the point that I was 28, 27. but I was doing my PhD and it was on the Muon GS2, but it was, you know, theory side of things. And I decided that I wasn't enjoying it as much as, you know, the experimental side was really interesting me. And so I kept saying, oh, okay, well, can I give this talk here? You know, can I go to the US and give this talk? Can I give this talk? Can I, you know, go and meet the experimental physics department at Liverpool? And when you do that, when you make those steps to not only know other people, but make yourself known, and you start to you get that exposure, it's, you know, if you're committed enough and you're dedicated enough and you have the drive to do it, you can basically do what you want, right? You can get anywhere you want to go, and it's a big wide canvas for things that you can do. So yeah, just apply yourself in where you want to go, and you can probably get there.
And also don't think that the field is full of geniuses. I don't think I've ever met a genius, right? I've met many people who think they're a genius, right? But I don't think I've ever met one. So most of the people I know who are doing great science just work hard.
Yeah,
so,
I'd second that. It's all about how you want to apply yourself. A lot of it's a process, right? A lot of it's doing the same thing, and it can be quite technical, but over and over again until the point where it feels like it becomes second nature.
Yeah, that's some very good advice. We've just had a question come in again. It's another, I've got a couple more specific ones after this, but this is another sort of a more vague general question. It was sort of, what would you say is sort of the biggest problem facing particle physics at the moment? I guess they're referring not to there's obviously what we don't know, but is there specific sort of specific problems that need to be resolved that haven't got there beyond the sort of the standard models? Not enough. Typical answer.
You mean in terms of physics questions that we don't know the answer to?
Yeah.
Oh, yeah. I mean, there's I wouldn't say they're the obvious ones, but there's the ones which we've been trying to find answers to since about 1980. So we don't know where all the antimatter went at the start of the universe. It disappeared in 3 minutes, and it shouldn't have disappeared. So there's another interaction out there which violates CP, which is interacting with antimatter different than matter, and that may well be in the neutrino sector. That's why, you know, Justin's doing June. We've not seen a dark matter candidate at all. We don't, you know, nobody's seen any compelling, you know, there's obviously rotational curves of galaxies and various other things, but nobody's seen a particle which can explain what dark matter is. We've got no compelling theory to unite gravity and, you know, and quantum mechanics. So there's no real understanding of quantum gravity. So there's plenty of things out there that we don't understand. And also all the theories that we have mathematically, they diverge. They, you know, if you move them up to high enough energies, they produce nonsense. And so there has to be other interactions and particles out there just from a sort of mathematical point of view. And that's the motivation for, you know, extra dimensions or extra symmetries, supersymmetry, or whatever what you want to say. So I actually, strangely, I think I started my PhD in 1988. I don't think we're any further along, to be honest. We've discovered the Higgs boson on the top quark, and we know that neutrinos oscillate. So they're the three things that have happened in 30 years. But we sort of suspected all those things were probably going to happen, or well, maybe not neutrino oscillations, but were there. And the big questions were still groping around, unfortunately.
No, I mean, you know, neutrino oscillation was discovered by accident.
Yeah.
On the way to trying to answer one of these big questions that still haven't been answered.
Yeah, proton decay.
They were looking for proton decay. So you know, proton decay is the classic signature of a grand unified theory. So that's applying the strong interaction together with the rest of the interactions in one theory. We haven't solved that yet. We've never observed proton decay. But the first neutrino experiments, like IMB, Kamiokande, those sorts of experiments, had neutrinos were a background. They were set up just to look for protons inside a detector decaying. You know, the neutrinos coming from the atmosphere were a background. Then they noticed there weren't enough coming from certain directions, and all of a sudden you've got neutrino oscillation. But you know, that fundamental question, is a grand unified theory, still as open as it ever is, and it's still, you know, one of the science goals of Dune, alongside the other stuff we've talked about, is to look for protons decaying. You know, we're still back on that question.
Yeah, And a lot of these theories of what tends to happen with theoretical physicists is if they see that your collider, let's say the LHC is being built and it has a sensitivity to a certain mass scale, let's say 10 TeV, their theory of explaining a unification or whatever will magically predict a lot of things which occur between 5 and 10 TeV and not things which occur at 40 TeV, right? Because they want to be vindicated. But some of this is, there are some natural scales out there where you expect things to happen, but there's a huge parameter space of out there which is yet to be explored, and it's difficult. So
the next one, I guess, is very much aimed at Justin. So someone's asked sort of just to maybe give a brief overview of how technically how we actually measure the mass of neutrinos, or rather put upper bounds on what the mass of neutrinos might be. And I don't actually know a lot about June, so I don't know if this is something you're doing in June or if that's more focused on sterile neutrinos, but I assume you might know a bit about it.
That's actually a more subtle question than the person asking the question probably thought it was. So what we do in June is search for a process called neutrino oscillation, which is how, the rate at which neutrinos change from one flavor to another. So we make a beam of Muon neutrinos at Fermilab, and by the time it gets to South Dakota, pretty much half of them have turned into tau neutrinos and a few of them have turned into electron neutrinos. The rate at which that happens tells you the difference in mass between neutrino states. Okay, so it doesn't actually tell you the absolute mass, it tells you the difference, the delta. So, neutrino oscillation would look exactly the same if all the neutrinos had a mass of a GeV, or the neutrinos had a mass of an electron volt, but they had the same differences between them effectively. And so what we're doing with Dune doesn't actually give you any information about what that scale is, what the upper limit on the mass of a neutrino is. It tells you they have mass because they're changing. So in order for something to be changing, it's got to be going slower than the speed of light. So if you're going at the speed of light, your time dilation is infinite, you've got no internal clock, so you can't change. So we see something change, so neutrinos are going slower than the speed of light, therefore they've got mass. But it doesn't tell you how much mass. To actually get the limits on the mass itself, the absolute mass as we call it, there you need to go, there's two ways that we get information on that. So one is from beta decay endpoint. And so that is, so there's the leading experiment at the moment is called Katrin, and that's in Germany somewhere. I forget where in Germany, it might be Heidelberg, either way, in Germany somewhere. And basically what they do is they have a sample of tritium, which undergoes beta decay, and you just look at the spectrum of the electrons that come out, and right at the high energy end of the spectrum of electrons, that's where all of the energy of a decay has gone into the electron, and none of it's gone into the neutrino. So the neutrino is stationary. And so the very highest energy electrons will have the energy available in the decay minus the mass of a neutrino, minus mc squared. And so you're looking for that high energy point of the energy spectrum. And so that's actually what's told us that the absolute mass of a neutrino is less than 0.1 electron volts. It's that measurement. The other source of information on that actually comes from cosmology, from the cosmic microwave background. So the Planck satellite has given us a sort of similar-ish limit on neutrino mass, that sort of 0.1 electron volt region. And that's basically by looking at the power spectrum of the cosmic microwave background, the fluctuations in the early universe. And at its simplest level, the very early universe was this hot dense plasma, and one of the things flying through it were neutrinos. And depending on how much mass you've got, that depends on how much the neutrinos wash out those fluctuations effectively. And so you can reconstruct back from the cosmic microwave background a limit on the mass of a neutrino. So you're sort of pulling all of these things together. So you get cosmological and beta decay limits on the absolute mass. Then Dune neutrino oscillation experiments tell you about the differences in mass, and you're sort of trying to tie all of these bits of evidence together. That's sort of how it works.
Yeah, definitely. This next one's aimed at Alex, although I suppose if Mark and Justin can remember how they got into particle physics, they'll feel free to answer as well. But so what first attracted you to particle physics in particular? Was it sort of a module, a lecture, or a specific book? And I know, Alex, in this case, it might be quite interesting because obviously you switched from theoretical to experimental, or you're now doing.
Oh, yeah, I mean, I don't know. I just floated, I think. I did an astrophysics undergrad, which is probably the greatest sin of my life so far. And then I went and did a physics master's. And that was interesting in the sense that I didn't, so when I finished my undergrad, I didn't know, it's a bit like what Justin was saying about doing an MPhys and getting a feel for what, you know, I did finish my undergrad. I didn't know if I wanted to stay in physics. I didn't know if I wanted to do a PhD. And so my university, I was at Queen Mary in London, and they had this nice program whereby you could do a 2-year master's, but the first year was taught, and the second year gave you a year-long research program where you were kind of sat in an office, a PhD office, to do an independent project, and you had to write up a report. It was, you know, 20,000 word report at the end of it, and you know, you had to do a mini viva and all that kind of thing. And I think that in the end was what convinced me that I really enjoyed it. You know, research is difficult in the sense that it's not like you a lot of the time, especially if you're doing theoretical physics, you have to sit and motivate yourself. But even if you're sat here at the desk, especially doing data analysis, there's no one behind you. You're not reporting to a manager. There's no one really telling you, you know, this is what you have to do by this time. And so you have to have the motivation to do it. And finding out you have that motivation is a big key. And so that then led me to apply to PhDs. And I went to Liverpool, obviously, and I did that. And yeah, I mean, I was really lucky. Doing PhDs it's not pot luck, but you should you know, sometimes you can have a really, you can some projects are better than others, and some supervisors are better than others, and not necessarily the supervisor's better, but the relationship between the student and the supervisor. I mean, it's 4 years and it's fairly intense, and so you hope that it's good. And I was really lucky. I had a great supervisor who gave me a very well-defined project, and I really enjoyed it, and that pushed me to you know, apply for postdocs. But none of these I don't think any of these paths are defined in the sense that you always have to move on from one step to the next. I seem to have followed that path, but you know, at any point you can diverge. It all just depends how much you really enjoy it at the time. And so over time, for me, I think the enjoyment has increased and my interest has increased, which has led me here.
I think my story is less evangelical than Alex's. So I'm old enough where you didn't even do 4-year degrees, you did 3-year degrees, and you didn't do a project. And I hated my undergraduate. It was really tedious. I thought everything in it was boring as hell. And I was doing it, and I didn't even think of doing a PhD. And then I started applying for jobs. I had no idea what job I wanted to do. So I started applying for things which were like sciencey jobs. So I went to try and get a job with, at the time, it was called the Central Electricity Generating Board. And I sat there being interviewed by all these people, and all these people were doctors, and mostly morons actually, but they were doctors. And I remember sitting there going, how do I progress in this company where, you know, and it became obviously apparent there that in order to progress, everybody interviewing me was a doctor. So I thought, well, sod this, I'll just go and I'll do a PhD. And that roughly coincided with a time in the 3rd year when I did a physics option, and I was actually taught by somebody external from where I was. Somebody at the Rutherford Labs taught me, and they were a practicing particle physicist and knew what they were doing and had a real enthusiasm for it. And that was it. And I thought, oh, this is great, but they'll never let me in. But I applied and got in. And then I think, like Alex, then at that point, when I actually started doing it, I had no idea what it was going to be like. But then when you start doing it and have some responsibility and find, oh my God, I'm the only person who knows about this, or at least I'm the only person who knows how to turn this piece of apparatus on and maybe, you know, stopping it catching on fire, then can be, you know, it's exciting and it's challenging, and then you enjoy it. And then at that point, you just move on because you go, I'm enjoying this. What should I do next? So I sort of fell into it. I don't think I did an evangelical, oh my God, I want to do a PhD. So I think it's a lot better now that you can do in the 4th year, because you get to experience some research and see what it's like, and you know, you can choose then whether to do it or not. Whereas I didn't have that opportunity.
I went in through the fairly standard NPPS project route effectively. I was, it sort of started my 4th year of my undergrad. The NPPS project list was out and trying to choose projects, and I think a couple of days before I happened to have one of the particle physics lectures was on neutrino physics, and I thought, oh, that's quite cool. That was a fun lecture. I'll do that. And so I just sort of chose a neutrino physics project from that. Got on really well with my supervisor, and stayed, applied and stayed on and did a PhD with them. So, I guess I did a fairly standard route into it. But again, if I'd happened to have had a lecture on Atlas a couple of days before, or a lecture on something in condensed matter physics a few days before choosing projects, I might have made a completely different decision. You never know. But yeah, again, it was just get some experience and get to know people. Is basically how it worked.
Fantastic. Yeah, it's all very encouraging. Looks like it's possible for you to do it if you have enough motivation. I think we'll round out with one final question, and this is probably aimed towards Alex. And you mentioned it briefly in passing, how there were sort of different theories, a lot of different theories that could explain the anomalous magnetic moment. And I know they'll be very complicated, being supersymmetric particle physics theories. But if you wanted just to give sort of a brief idea of if there's a particular one of these you think is best suited in your opinion, or are there any particularly interesting ones, or anything you can just summarize briefly?
Yeah,
If you want to go too far.
I kind of touched on it already, but my bias is definitely towards low energy physics. This thing that Mark was saying about how we have theories that diverge at very high energies. Well, for QCD and the strong interactions, the theory diverges at very low energies, which is why we have non-perturbative physics for quark models, right? We can't calculate that because the prediction of the coupling constant for hadrons starts to diverge at very, very low energies. And it's an area of physics that hasn't had, I would say, enough interest. Well, it's definitely getting more interest now, but the reason that it's becoming more interesting is because we have lattice QCD now. And lattice QCD is a way of it's a calculation by which you take space-time and you discretize it. So instead of doing these calculations for observables, so say you want to measure, I don't know, this coupling constant or the mass of this particle or the anomalous magnetic moment, for example, when you do that in a standard phenomenological approach, you do that over a continuous space-time, okay? But we can't do that generally for hadrons. And so what you do is you discretize space-time into a grid. And you put that grid in a finite box as opposed to an infinite space-time, and then you calculate the observable that you want to calculate on those points. And then once you've done that, then you do an extrapolation whereby you extrapolate out to an infinite volume, and you make your lattice spacing infinitely small, so that you basically resolve back the continuous space-time that you wanted in the first place. And that's really interesting because it's a first principles calculation for low energy hadron physics, which we've not been able to do before. And it now is becoming, the problem with these calculations is they're incredibly computer intensive, and they use incredible computer sources that are very expensive. And so the precisions on them at the moment generally aren't that great, but in the next 10 or 20 years, they'll really take off. And at that point, you'll be able to compare the predictions for low energy hadronic physics with what we see from measurements. And even now there are inklings that potentially there are discrepancies at the low energy sector than we would more discrepancies than we necessarily expected there to be before. And that's true of g-2 and other areas of physics as well. So that's where I would stick my money. And there are a lot of models, like we said, Mark mentioned axions and stuff like that, and dark photons and dark Z bosons. They all exist in the low energy regime. And so are all models, there are lots of models whereby these are all interlinked. And, especially for g-2, because the energy is generally very low, they can all contribute in, loop insertions in that muon photon vertex and contribute in some way. So that would be where I would stick my money, but I'm not a very good bettor generally, so don't take my word for it.
Well, I think that's pretty much all the questions. I'm not getting any last ones in. So unless anyone else has a question they want to speak up or put in the chat right now, I think we're coming up towards, yeah, we just finished 1 minute ago. So if no one has any other questions, we can sort of round off the event. So just wanted to say a massive thank you to Alex for doing the tour and the presentation. I mean, it was fantastic. I found it really interesting. It's not an area of physics I know a lot about, being an astrophysics undergrad.
Oh no, see, I'm feeling it already.
But
Don't worry, you'll be a theoretical physicist and a particle physicist after that in no time.
And yes, thank you very much to Justin and Mark as well for coming on to Q&A. Some brilliant answers there. And yeah, I've enjoyed all of it, and I'm sure everyone else has. And if we were in person, I'm sure you'd get a round of applause. But
thank you for organising it.
Yeah, it's brilliant.
Thank you.
It's been a great event. Thank you for having me and for having also. It's been really good.
Thank you very much. And I hope to see you around the department.
Hopefully soon. Yeah.